All right. Guys, I want to redo the lesson I tried to do Friday. Because I think you'd all agree Friday just wasn't happening, was it? So I want to just take it from the top, okay? Pretend Friday didn't happen.
We actually know what's going on, kind of.
I think you guys will be a little better this time around.
Yes.
Okay, so you guys ready? Two things I need you guys to know how to do so far. The first one is you need to know what the square root function is. This graph right here is the square root graph. Okay, but the other thing we can do is we can take the square root of a graph.
So is there like a set range for that? Like that it will always
Like typically this graph here will be, the domain will be greater than 0, the range will be greater than 0. Does that make sense? Now we can move this graph around as well, right? But when we square root another function, that's where we get some weird looking graphs. Here's the first picture I want to show you guys. Imagine the blue line is a pre-existing graph. The red line is then what happens when you square root that function. So why does the red line not keep going past this point? You can't square root negative numbers, right? And so the output is the y value. All of the y values of the blue line over here are negative, so you can't do that. Where are the two invariant points? Well, when y is 0 and when y is 1. Okay. Look at some of these other values here. When this was at 4, do you see how it drops down to 2? When it was up here at 9, it'll drop down to 3. You don't really get that on your graph here. Does that make sense though? Like when this was 9, 9 would drop down to 3. 4 goes down to 2. Does that concept make sense? So these things are similar to each other, but like there's slight differences. Okay. So I want to walk you guys through just a bunch more examples. I know we already tried these ones, but let's say I gave you 2x plus 1 and x squared, and basically what this notation means is take the 2x plus 1 and square root it. Are you in the wrong notes, Carolyn?
Yes.
Those are the ones we're looking for. You're giving me funny looks there.
Sean, what are you teaching?
I don't know.
Yeah.
Hey, someone close my door for me. Okay, so if I were to square root the graph 2x plus 1, and I were to compare to the graph 2x plus 1, let's graph these guys. There's the graph of the square root of 2x plus 1, and here's the actual linear line. You're probably going to want to zoom in a little bit here, just to get an idea of what's happening. Zoom in right around here. Where does the square root graph start? It actually starts at negative a half.
right because you got to factor.
Because you gotta actually factor this thing. If you were to take the square root of 2x plus 1, if you were to factor out a 2, I know we don't normally do this, but if you factor out a 2, it would be x plus a half.
So why did we do it? Like, why did we factor to be half?
Okay, so that we know how far to move the graph that way.
Where it starts.
Because like, if you look at it like this, it seems like you should move the graph 1 unit that way, but it's actually not 1 unit that way, it's only half a unit that way.
So,
It still shows up on the graph the same.
Yeah, it still shows up on the graph the same, yes.
like, I just don't understand how we knew to square root it then in that particular one if we don't usually, I guess.
Square root or factor.
Factor.
You should probably always factor if you can. That'd be a good rule of thumb.
I just don't think she gets like why.
Yeah, but like typically we wouldn't square root that to half, so why all of a sudden now are we?
Maybe to prove why this graph starts here at negative 1/2. Maybe to try something different here.
It's just
If I took,
because we're factoring it to like a decimal number and we've never done that.
okay,
before.
how about this? If I were to say 2x plus 1, if it had to equal 0, then if I were to minus 1 from both sides, 2x would equal minus 1, and then divide by 2, x equals negative 1/2. What I've now proven to you is this is the lowest x value you can have. Does that make sense?
Yeah.
That's kind of what we're doing here, is we're trying to figure out where is the lowest value that we could have. I don't actually have to factor if I don't want to. Does that make sense so far? Okay. The domain of this graph then would be x has to be greater than or equal to negative a half. The range of the graph was y has to be greater than 0. Does that make sense? And I'm not going to do it right now, but if I wanted to solve the invariant points, find where these two graphs cross. Does that make sense? Because you can see they cross like here where x is or y is 0, and they cross here where y is 1. So I want to grab that back door too. Did we attempt this one last day?
Somewhat, yeah.
Okay, one of the points I want to make in this unit, guys, is that these non-polynomial functions, they are all going to look very different from each other. There will be some similarities, but it totally depends on what the graph is as to how it looks. So I'm just trying to give you a ton of examples of how these graphs could show up. So let's say we took x minus 1, no, x minus 2, x plus 1. I'm just going to graph that originally. That's a quadratic. What's going to happen when we square root this graph is you're going to get a big hole in the middle of the graph because you can't deal with all those negative y values. Does that make sense? So when I now actually square root this stuff, the x minus 2x plus 1. I'm just going to zoom standard this thing. Here's the quadratic. Do you see how like the actual square root graph looks something like this and
But it looks linear.
this? Well, it looks kind of linear. If you change the scope of it a bit, I promise you it is kind of curved, but you're right, it does look linear. Could you guys find me these values here for x then, like where it starts and stops?
Oh, not the invariant points, just where it says.
Yeah, where does it start and stop? It's your old x-intercepts.
This
Why?
is where we also have
Oh.
x-intercepts at 1 and 0.
Those are invariant points at 1 and
Yeah.
0, yes. Yeah. So one of the invariant points would have been right here at, what's that going to be, negative 1?
Yeah.
And also be 1 here at 2. So if I asked you for the domain of the graph, here's one way of writing the domain. You could have said x has to be less than or equal to negative 1, or x has to be greater than or equal to 2. That's one way of writing domain. Another valid way of writing domain is you're going to go from negative infinity to negative 1, or you're going to go from 2 to positive infinity. That's a valid way of writing it. That's your domain. What about your range?
Greater than 0.
Yeah, it's almost always greater than 0.
Is there a way that it's going to be structured on the diploma?
They'll probably do a mix of both, so I want to make sure you guys know both.
Just so they mess.
What's that negative, say, negative d?
Right here?
Oh, it's 1.
That's negative 1 close bracket.
So if you have a quadratic function,
Yeah.
you square root that quadratic function, the roots are the starting points of your square root graph.
Depends on how the quadratic looks, but yes. Because you could get some really weird graphs here. Let me go off the board a little bit here and try some other ones. I'm gonna ask you guys to find the square root of negative x squared minus 2. Try typing this one in. Find the square root of negative x squared minus 2. You getting anything? Negative x squared minus 2. Find the square root of that graph.
Didn't get it.
Why not?
It's the same.
Well, what does... So this first graph right here, nothing actually shows up. This is what negative x squared minus 2 looks like. What happens when I try to
Because
square
it's all
root
a
it?
negative.
Everyone catch that?
Yep.
The graph is entirely in the negatives. Therefore, if it's entirely in the negatives and you try to square root every single y value, will you even get a graph?
It does, doesn't it?
What about if I give you a graph that is entirely in the positives? So what if I were to change this graph to x squared plus 9? And then do the same thing. Take x squared plus 9. This will be a graph that is entirely in the positives. Really weird looking graph.
Oh, okay.
Way up top right here is the parabola. And then the x squared plus 9 graph that gets square rooted doesn't actually like have any gaps in the graph, because like this value of 9 gets brought down to 3. And this value up here of 16 gets brought down to 4. So like, since there are no x-intercepts in the first graph, there aren't any like holes in the graph in the second graph.
So why is there no x squared shape or x?
There is.
The shape.
There is, it's just, it's way up here. So like this is where your parabola is. And then this is where the square root of that graph goes to. It almost like it flattens out.
But why isn't the square root graph? Like the little one that looks like this. She's talking about.
So the reason why it doesn't do that is because on those graphs there actually were x-intercepts. And like x-intercepts, like,
Okay, yeah, so x-intercept means.
okay,
it's
so like,
that.
say it's this graph right here. Okay, if you square root this graph, it's gonna look like this and this, and you'll have a big gap in the middle. Let's say that your graph was this, and I ask you to square root it.
You can't.
You get nothing, because that's not doable. So there is no answer. Let's say I give you this graph right here. Well, what this graph here means to do is take every single y value and make it the square root of itself. So like here, this guy's square root comes down to here, and this guy's square root comes down to here, and comes down to here. But why would there be what number would there be that there's like a gap in the graph? Does that make sense? Like, because there are no x-intercepts. So therefore there's no like place for the graph to start and stop.
Why is it going like this and not like?
Yeah. And
Well, because what ends up happening is each of these y values right here gets pulled down. It's almost like it's compressing it down, but by the factor of a square root. So like this y value is 9, now it's 3. This y value is 16, now it's 4. This y value is 25, now it's 5. So like, it's almost like this graph kind of flattens out, and it almost looks linear at this point here. It's not quite, but
There's all of the original being positive. There's no way it will be negative.
so like it almost looks like an absolute value graph, if that makes sense. Like here's a quadratic, and then all of your values are square rooted. So if I go to my table, 9 square roots down to 3. Gotta find another one that actually square roots. 25 square roots back to 5. That makes sense. And so all of your values are getting pushed downwards. One more thing here, okay? The thought I want to make here is that I can't let you know what any square root graph is going to look like, unfortunately, because it totally depends on the graph you're given. Does that make sense? So I want to give you kind of the skills to interpret it, but there's not really like a pattern to this that we can work from. Okay. If there's only one x-intercept, it's probably like a linear graph. What would happen then is all of these negatives right here we wouldn't work with. And then this graph usually does something like this, where all these values get pulled down. Oh, good point. Okay, let's do that one. So if I were to give you, let's go with x. I get what you're saying. Let's try bracket x minus 3 all squared. That graph would look like this. Does that make, that's what you're asking?
Yeah.
Okay. So then if we were to do the square root of x minus 3, need to put another bracket in here.
Oh.
All squared.
If your squares made the root of that,
It would look like this. Similar to the other one we did there. If that makes sense. Where all of these y values are getting pushed down. And essentially it makes it look kind of linear, doesn't it?
Yeah.
Where like the new graph is like almost a straight line. Does that answer your question?
Yeah.
Okay. Let me fast forward here then to a new example. If I were to give you just some random looking graphs then, could we sketch what the square root of these graphs would look like? Let me try a couple with you. So here's an upside down quadratic. Where would the graph not exist when you square root it? Okay, so like all of this stuff right here and this stuff right here, I can't do anything with that. Does that make sense? So, and then start taking all of your y values and start square rooting them. Right here I have a y value of 0, so it wouldn't move. Because this is an x. Oh, does the xy axis show up for you there?
Yeah. Oh, kind of, if you look.
I thought.
So like
Oh, that's a y
here's a
value?
y value of 0.
Okay, yeah.
Okay.
Just square
Here I have a y value of 1.
One.
Okay. Here I have a y value of 4.
2.
Okay, so pull it down here to 2. Now, you can't really do numbers like 3 all that well, right? But like 3 would kind of come down a little ways as well. So it could look like this. And then here's back to 1, it wouldn't move, and 0 would stay the same. This graph would look kind of like this. Does that make sense? Basically what's happened is this parabola that used to go in the negatives, only the positive part of it I kept, and the rest of it just kind of got squished down. Okay. It actually is going to come slightly outside of the graph right here. We talked about that last day a bit. The reason why it does that is when you square a decimal number, it actually gets larger. You guys remember talking about that? So,
Why didn't it do the whole?
Why didn't it go?
Yeah.
well, because these numbers over here were negative. Like the graph didn't go till infinity for forever. So all I had to do is take all of my values and kind of cut them down a little bit. Can I try the next one with you guys? I think I can answer your question there. Where will this graph not exist? Okay, so this part right here won't work. It also won't work right here. So now start looking at some of your y values. Here there's a y value of 0. It won't move. Here there's a y value of 1. It won't move. Here there's a y value of 4. So it'll come back down to like 2. Here there's a y value of 4. It'll come back down to 2. This is a y value of 5. So it's going to come down to whatever 5 square root is. Okay, so like here. Here's a y value of 1. Here's a y value of 0. So part of our graph basically involves this graph right here getting, like, it's like someone sitting on it and squishing it. Because all of your y values are now square root. But it's the second half of the graph that kind of keeps going then. So then look at the y values over here. Again, you have a y value of 0 and a y value of 1 that don't move. A y value of 4 comes down and becomes 2. Here, there's a y value of 9. It'll now become 3. And this graph will kind of keep going. And so what will happen is this will be the part of the graph that keeps extending like this. To me, this graph looks like an Ogopogo monster underwater. I don't know whether you see this at all, but the graph would look like, just start over again. The graph looks like this. Comes out of the water for a little while, goes underneath, goes under the water for a while, but we can't do that, and then picks up like that. Does that make sense? That's what this graph would look like. There's not really a pattern to this. Like, I can't give you like a foolproof, if this, it's this, if this, it's this. The skills I'm trying to show you are basically, if the y values are negative, the graph doesn't exist. If the y values are either 0 or 1, they don't move. And if the y values are numbers like 4, pops down to 2, 9 comes down to 3. Does that make sense?
So if you kind of like, even though you said it can't be necessarily this or this, but like if you had like a negative parabola, like in the positive, then the new
Like
one would
this?
look some sort of like inside of it,
Yeah,
kind of inside of it.
that's a good way of looking at it.
And
Like,
if you had a positive parabola, it's kind of gonna go out.
if you had a positive parabola, it'll look like this kind of. Like, there are some rules we can use, but I don't really think I can give you like a catch-all that would work. There's just too many possibilities. Okay, let me try one more, then I'll have you guys do the last one. So here's a graph that looks like it's probably a combination of absolute value stuff because it's all linear. The graph won't exist here, and it won't exist here. This point, where y is 0, won't change. this point where y is 1 won't change. And then hopping over here, again, this point won't change, and this point won't change. Does that make sense there? So those 4 points won't change because their y values are 0 and 1. It gets as high as 3, so what's the square root of 3? 1.7? So this 3 will come down to 1.7. So your graph will look something like this, I guess. And then over here, as this graph keeps going, it'll pick up again when y is 0 and when y is 1. And if this graph could, it would keep going that direction again there. So it's kind of like the Ogopogo one underwater again, where he's over water for a while here, and then he disappears underwater because you can't square root those negatives, and then it picks up again. Does that make sense? You guys try the last one. See if you can get it before I do it. That won't change, that won't change, that won't change, that won't change. So this graph should look roughly like that. With one more thing, actually.
We want it 0.
There will literally be a single point right there. Because it does touch 0 and you can't square root 0. So this will be a really weird graph. You'll have a little bit of like a hump coming out of the water right here. And then this point right here where it touches 0, it will just be a single dot on your graph. So if you were graphing this, it would look like this dot.
Why do you only square that? Why wouldn't you square that? Square it.
Because what this thing says to do is you have a function, and it says to square root the function. The function though is y. Does that make sense? So what I'm asking you to do is take all of your y values and square root them. We could do this. I could say, tell me y equals f of square root x. And what that would mean to do is square root everything in this direction. We don't do that. We could, but that's not where the curriculum goes. Does that make sense? Because all that would do is just take all your values this way and squish them in like so. Whereas what we're doing is we're square rooting them this way. You guys get the concept? Because I'm now going to give you some more challenging questions. Okay, like more typical of what I'd ask you. So like, here's one that I might ask you on an assignment. Here's some points on the graph. And then what I'm going to ask you to do is take the points on the graph here and square root them. Tell me what the new points would be.
You skip the one that negative, right?
Yeah,
Negative y.
like negative y's. So for example, 0, 4 would now be at 0, 2. Does that make sense?
Wait, all the
What
x's
about
stay
what
the
we can do
same.
for 8 and stuff? Like,
Okay.
Did you
Okay,
finish
couple
that?
questions at a time here.
You didn't finish that.
What? Finish what? First
You
point is
did.
done.
So the first point, like the point is 0, 4. So the y value gets square rooted. So still x is 0, but now the y value is no longer 4, it's now 2.
If you came to your
You're just taking the y values. We're only square rooting the y.
Yes, but like I'm looking at this g of f back.
Oh, okay. All that means here is that you have a function, and I'm now asking you to square root the function.
The function
We-
of g of x is to square root x.
Now, like, I don't know what the equation is, right? Like, the equation could be x squared plus 5x plus 6. I don't know what the equation is. But what I'm suggesting for you to do here is take your old function and square root all the numbers. But we're just square rooting the y values, though.
Square root your last one.
So do you leave all the x's the same?
Because g of f of x here means take all of these values right here and square root them all.
Like to me that means if you're square root x.
No. Because g of f of x means like g of, like, f of x is your y value. G of, my goodness, I can't write here. G of f of x means square root all your y values.
Sure. Okay.
Okay, this next point here, 1, -5, can we do anything with that point?
just be error.
error, sure. 2, 8 will be 2 root 8. Just leave it as root 8.
Oh, that's easy.
That's fine.
And then 3.
You could, by the way, make it 2 root 2. I'd accept that as well.
'Cause it's simple.
But don't give me a decimal number. I don't need the decimal number. 3, 9 would turn into 3, 3. 4, 0 would stay 4, 0.
Okay.
And then 5, negative 2, you can't do anything with? Does that make sense?
Yep.
That's something more typical to what I'd ask you. We've done this before, right? Just with different types of functions. Okay, here's a graph. We're now going to do g of f of x. Okay, so g of f of x, just so you know, like what we're doing is we're square rooting all of this stuff here. There we go.
Maddie Hearn, please come to the office. Maddie Hearn.
Can you guys now find me the domain of this graph?
Algebraically?
Square.
Yeah, but you have to square, like, not just the intercepts.
Good. It's just the intercepts.
Oh.
What does this original graph here look like? It's an upside down parabola with intercepts of
Negative 3 and positive.
-3 and +2. So -3 and +2. This is what the original quadratic graph looks like. So if I want the domain of this graph when I square root it, what's the lowest number I can use for x?
I mean,
No, -3.
okay.
Yeah. And what's the biggest number I can use for x?
2.
That's it.
Wait, what?
Oh,
That's it.
wait, what?
But then doesn't it do the whole out thingy?
Well, no, because what would happen if you square root this graph?
I feel like it's
If you square root this graph, like if you were to actually go through it, all these negative numbers wouldn't exist. And all of these values will just become like shrunken in.
So then what the heck is the outie thing?
Okay, well, that would occur in a graph that, say, looked
Upside
like...
down?
Well, why don't I go with a linear graph for right now? If I gave you a linear graph like this, then what would happen is all of these values, like here it was 3, it would come down, and this one would come down,
But
and this one would come
if our
down.
parabola had a minimum, then would it do that?
Um,
You're talking about this?
yeah, I think that's what you're saying here. Let me try drawing that here.
Then-
I don't want to stick with just parabolas though, because we can do this for all sorts of things. But let's say it looked like this.
Yeah.
Your graph then would do this
Oh.
and this kind of thing. Does that make sense? Okay.
Okay, so and then we
Okay.
just, what did we, domain, okay, we just found the domain.
That's actually all I asked you for.
And why is it in between two? B is dealing with X.
Well, because the -3 is the lowest x value that you have for an intercept, and 2 is the highest value you had as an intercept. If you went further than that, you'd get negative numbers.
And
Oh, one more thought here. Just want to jump in there, Amy. What if we tried a number bigger than 2? What if we tried a number 3? Test this out. 3 plus 3 would give you 6. 3 minus 2 would give you 1. So 6 times 1 would be 6. If you times it by -2, you'd get a negative number, and you can't actually square root a negative number. So that's why numbers bigger than like x is 3, x is 4, you can't actually use those numbers because you can't square root negative numbers. But any number between -3 and 2 should work. Does that make sense? You still have your question?
interval notation is just with the square bracket thing.
Yeah, that's where my next slides are going. Okay, I've already told you guys about this. Interval notation is the square bracket concept. It basically works like this. Low number, comma, high number. That's it. Okay, it's not hard. The way it works is that if it's a square bracket, you get to include that number. And if it's ever a curled bracket, you don't get to include that number. So basically what this means is that x has to be greater than 0, but x has to be less than 20. Or equal to. If you take off the or equal to signs, then convention is to use like a curled bracket rather than a straight bracket.
Which would include the infinity
Yeah, the infinity one is always a curled bracket, just because you can't really include infinity in a number.
Usually pull off, you forget about the whole bracket.
So let me give you some more examples here. Let's say you started at 0 and you included the number 0, and then went up to 4, but you didn't get to count 4. You'd write it as close bracket 0, comma 4 open bracket, meaning you get to count 0, and everything from 0, 1, 2, 3, and 4,
The 3.9.
but you can't actually count 4. You got to stop at 3.99999. Okay, that's just the way we phrase it. This notation right here would be another way of writing that x has to be less than or equal to 2. Because what this means is you can have all of the negative numbers in the world you want until you reach 2, and that's the last number you can have.
Close bracket.
Can you actually count 2 though? Yes.
Yes.
That's what this little close bracket means.
Close bracket.
And you know, that would test like maybe a Swiss knot.
Yeah, I need you guys to know that that was actually the twist they played on last year's diploma question. I was quite frustrated on it because pretty much everyone got it wrong. So I'm going to make sure I'm going to show you guys this because, I mean, it's so...
Did you not show it to him?
I did, but nowhere near enough detail that people remembered. You know, because like it was such a small detail. They used, like it was so mean the question they used. For multiple choice, the question was like A, it was like closed bracket, negative infinity 2, like this. Then they did this one. Then they did this one. And then they did this one. So mean, hey? Like the question was not testing whether you understand domain and range. It was testing whether you understand how interval notation worked. And so many kids got confused on it.
Let me just guess.
That already eliminates C and D, right?
Yeah, you can't really have these two.
But still, you don't
B and
remember. You don't remember that.
Season
Yeah.
Yeah. So anyways, I want you guys to be familiar with this because if they test you on it, I don't want you to get that question wrong. Because every question you get wrong is 2.5%. That sucks to lose 2.5%. I found these pictures online. Hopefully they help make sense of things. If it's from A to B, including, it's square brackets. If it's from A to B, not including, it's... I like to call these closed and open brackets. If it's including A but not B, it's this guy. Anyways, you guys get the concept? Hopefully you can follow this. I don't need to do all of them. Let's just do two last questions. We'll call it a day. So if I give you a cubic function and then I ask you to square root that cubic function, can you guys tell me the domain?
Don't we have to like
Wouldn't hurt to, but you can use your calculator.
Oh.
Because your calculator would tell you where the where those are. I said algebraically. I guess you guys could do.
Element of the real. That's always the legit.
Okay, this guy's a cubic though, right? As a cubic, chances are the cubic looks something like this. Does that make sense? So then you've got to find where these points are on the graph where it crosses.
Close to most of that.
Okay, but then what is this thing? So determine the domain of the domain of square root of blah,
Of all that
blah,
stuff,
blah,
yeah.
blah.
So like type it in your calculator to start. Square root all of this mess. X cubed minus 3x squared minus 18x minus 60. Zoom standard to graph. And then we got to interpret what the heck this graph says, because does yours look anything like mine?
No, I mean, yeah, it does.
And that's hard to understand.
Yeah.
So it may be better then to, let's graph this thing then without the square root sign. Like, do the exact same graph, but don't put the square root sign on there.
You can do Zoom standard.
I'm getting this now.
Yeah, I get that.
Try zooming out then. Zoom out. Because we should get a cubic that looks something like what I've got here. Maybe. Zoom out again. It should look like a cubic somewhere. Oh my goodness. Oh yeah, that's not working.
Zoom out more.
Let's go. Yeah, we're really gonna have to change our window.
Oh.
What?
Go to the. It's not stopping.
Did I mistype this thing? X to the third minus 3x squared minus 18x minus 60. Okay, this isn't working very well, is it? Is anyone else having luck getting a graph showing up?
I just got like a line trying to
Okay, let me try something different here. Let's try, I'm gonna try to find the roots of this thing here by going to my table. I'm just gonna see where it equals 0, because maybe I designed the question wrong. Okay, you know what, guys? I probably made the question wrong.
And it doesn't equal.
Because the point I was trying to make, like there should be a 0 in there on a nice even number. I must have screwed up somewhere. What if I made it plus 60? Maybe that'll change the graph. Bah. Okay. Scratch this question, guys. The point I'm trying to make is not working.
So, did you root it?
The plus 60 kind of works.
Okay, hypothetically, let's say the cubic graph looks like this, though.
Kind of works.
Okay, like would it make sense that a cubic graph should look like this? Because normally there should be 3 roots to it. I must have made some sort of weird graph. Let's say one of the roots is at -6, one of the roots is at 2, and one of the roots is at 4. So scratch all this. But let's say this was the equation here. Could you guys tell me the domain of this thing when you square root it then?
Yes.
Okay. Over here, what numbers are less than -6? Can you actually square root those numbers?
No.
Okay, but you can square root every number between -6 and 2. So what you could then say is that your lowest number would be -6, and your highest number would be 2
For that one.
for the domain, for that one little section right here, right?
Why can't it be all?
Oh, I'm going to get back to that part. You're right, though. Then between 2 and 4, can I use any numbers between 2 and 4?
No.
Say no. But you can then pick up again at 4 and go to positive infinity, which gets like an open bracket. I'm okay if you use the word or in between here, but chances are you're going to see the letter U. U stands for union.
Make me think of going underneath it.
The notation that you may see would be this, a U in between it. And all that means is that it could be this or this, U meaning union. That's like the notation they use sometimes. Does that make sense? Sorry I kind of goofed on that question.
Interval notation just means to find the x values, right?
Yes. Now, by the way, I mean, you could also write it like this. X is between -6 and 2, or X is greater than 4. Like, I'm fine if you write it this way up top as well. I just want to make sure you guys know how to answer it the other way in case they try to mess you up this year again. Does that make sense?
That's interval notation too?
No, this down here is considered interval notation. This, I don't even know, I don't know what you call that. But like, this is what you normally learn domain and range as. I just want you guys to know this. Just in case.
Pretty confusing.
Alright, let's do one last one, call it a day. Okay, let's say I give you a point, -24,9 is a point on a graph. I want you to tell me where that point is going to be after you do a lot of different things.
Do you already know what it is?
No, I don't actually.
Oh.
Sorry, you're a little ahead of me.
Right.
Okay, first thing we should talk about, is this graph properly factored in the one location it should be? Okay, so before I do anything, I should deal with -2 square root of f of 3x minus 2 plus 1.
Why did this crack?
So let's talk about how we can move this point around on the graph.
What's the F mean? I've always.
Function.
It means I don't actually know what the function is. Like, it could be a square graph, a cubic graph, a quartic graph. I don't know what it is. All I can tell you is that there is a point over here at -24,9.
Okay.
What's the -2 going to do to the graph?
Over the line.
Over and stretch.
Okay, so which number will that change? X or Y?
Y.
Okay, so your Y value was at 9. Now it'll become negative 9. And when you times it by 2, it'll become negative 18. I'm just going to make a running tally. So this guy will now be at 24, negative 18. What does the square root... Oh, hang on. I should do the square root first, though, shouldn't I?
Oh no.
The square root should happen first, because that's the whole point of this graph here. So before I deal with this 2 and before I deal with this 1, would it make sense that I should square root the value first? Because I can't square root negative 18 now, can I? So take your Y value of 9, square root it down to 3, then times by negative 2.
Why would you square root it? The square root affects the Y as well.
Yeah, well, that's what the square root here does, right? The square root here affects the Y values.
Does it not
What?
affect the X value?
No, the X value will stay the same, just the Y value.
Oh.
So, okay, so this square root sign right here is going to affect your Y values. So all of your Y values will now be square root. So your Y value of 9 will now become 3. Then the negative 2 in front will take that 3 and flip it down to negative 6. And then the plus 1 will move it up to negative 5. Okay, so negative 5 is our Y value.
You don't worry about the 3x minus 6.
Well, that'll be your X value, because this will be inside the function. So then this 3 right here will squish all of your X value points in by a third. So 24 cut in third, it'll now be 8. So negative 8. And then move it over 2 that way, negative 6.
I got it.
Wait, do that again?
Sure. Should I take that from the top? Let me do the X value first. This 3 right here will affect the X value, squishing everything in by a third. So negative 24 will come into negative 8. That's divided by 3. Then the minus 2 will move it 2 more that way. So minus 8 will now become negative 6.
How'd you get the negative 5 for your?
Okay, so those are your X values. For your Y values, the things that will affect your Y value is the negative 2 sign, the plus 1, and the square root, as we've been working with. The square root only affects your Y values.
Oh, yeah.
Okay. So the square root's going to apply first. Square root 9, down to 3. Times it by negative 2,
Negative 6.
so that flips it from positive 3 down here to negative 6. And then the plus 1 brings it back up to negative 5. Okay. Now, I don't actually know what the graph is, so you can't test it on your calculator or anything. But this is the kind of question I might ask as well.
So the negative 2 flips it and
And makes it like twice as tall. So like what was going to be a 3 now gets times by negative 2. So like let me try to diagram this point's motion as we go through all of this. The point was at negative 24, 9. I square rooted this thing. So that brought it down to negative 24, 3. So I made it smaller. And then I flipped it over the axis, which made it negative 24, negative 3. Made it twice as tall, which made it negative 24, negative 6.
Okay.
Then I moved it up 1, which brought it to negative 24, negative 5.
Okay.
Then on the inside of the brackets, then I dealt with the 3 and the 2, which the 3 cut the negative 24 down to negative 8. So then it moved into negative 8, 5. And then the minus 2 moved it over 2 more to get me to minus 6, minus 5.
Okay, so if we would have done the x-axis stuff first, it doesn't matter.
Not really, yeah. You just have to do the x-axis stuff independently of the y-axis stuff. That make sense? Okay, let me summarize and then we're basically done for the day. Here's the 2 things I need you to know how to do. It really does break down into 2 things. I need you to know what the what the square root of x graph looks like. The square root of x graph looks like this. Okay. Normally, its domain would be x is greater than 0. Its range would be y is greater than 0. But I can move this graph around by doing something like, say, 2 square root of x minus 3 plus 6. This makes it taller and moves it like over and up. Does that make sense? The other thing we can do is I can give you a function. So I can give you, like, say, the function x squared plus 5x minus 9. And I could have you square root the entire function. All this means to do is take all of your y values and square root them. If your y values were negative, you can't do anything. Where are the invariant points?
At the intersection.
Which are where x and y are both. Sorry, when y is 0 and 1. Does that make sense?
Is there a possibility of more than just those ones?
They could happen in multiple places. For example, I could ask you to square root this graph, and then you'd have an invariant point here, 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 there, 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 there. Say that touched. You could have one there, 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 and there. So like you could have lots of invariant points.
But like, there's not going to be one at like 7.
No, because 7 does not square root to stay 7. Only
Right.
1 and 0 do. Does that make sense?
Yes.
Okay. I know there's not a lot of time left today, but here's a running list of some questions you can try. Tomorrow I'm going to move on to a new topic though. And Thursday actually. I need to cover some topic material, okay? No, I'm on question 2.
Woo!
I'll try to get them done soon. It's actually the top of the pile, so I'll try to finish it tomorrow. Any questions? Is this better than Friday? Get it more? Whatever this was, only not working. No, the next 2 days we're going to talk about rational functions, which are fractions, and how fraction graphs look.
Are they way different?
Guys, the one point I want to make in this unit here is that all of these graphs that we're going to work with, there's not a lot of rhyme or reason to them. Like, they're going to look weird and funky all the time. Like, every single graph looks different than the one before. Like, there are some similarities, yes, but like the non-polynomial functions are very different, if that makes sense. So I really can't give you like hard and fast rules that always work. Okay.